Let's talk about sketching the graph of a derivative. So all the sketching that we do in this video will be mostly based on the information you can see at the top of the page here. So if the original function f is increasing, then its derivative is positive. And if the original function is decreasing, then its derivative is negative. The first thing to clarify here is which way we're looking at the graph, because increasing and decreasing kind of change depending on how you're looking at it. So when we use those words in math, we always mean from left to right. From left to right, like we're reading words, right? So for example, this graph down here, this part of it is decreasing from left to right. So this is a decreasing graph, and we only look at it left to right. The other thing to clarify about this is that when we say the derivative is positive, what that would mean for the graph of the derivative function is that it literally the y values of the function are positive. So the derivative being positive means that the f prime graph is above the x-axis, like up here as opposed to down here. So these would be positive output values for the derivative. And then negative, of course, would be the opposite. It would be below the x-axis. Yeah, the only other details I want to clarify before we jump into a handful of examples down below is just sort of like the switch points. So anytime we're given the directions, like here's a function f of x, sketch its derivative, the first thing we're going to look for is like the important individual points on the graph. So those points will be where the derivative is either 0 or doesn't exist. So let's kind of organize what that would look like. So if the derivative equals exactly 0, that would be either at the top of some kind of bump or the bottom of a bump. That's where your derivative is 0, because it would have a horizontal tangent line with slope 0. And then there's two different ways for the derivative to not exist while not just being a discontinuity in the graph itself. So that would be corners and then vertical tangent. So a corner is going to be something like, if we scroll down to the bottom here, my last example has 2 corners in it. So at each of these points, we'll say, oh, the derivative doesn't exist there. And I don't have any examples in this video, but there will be one on the practice worksheet. A vertical point, so instead of a corner like this, we'll have a vertical kind of moment where the graph could go up and then over. So you have like this one point where its tangent line would be a perfectly vertical line. So when it's the corner, this will correlate to a jump in the graph of f prime. And when there's a vertical tangent, this will correspond to a vertical asymptote in the graph of f prime. All right, let's start our first example, which you can see below. So we have the graph of this function here with minimal labeling, and we're asked to sketch the graph of its derivative. They always say sketch here instead of like perfectly graph its derivative, because we're going to show some important features of it, but it's not going to be a perfect, computer level graph. So the first things we want to indicate are what I was talking about here. Where is the derivative 0 or not existing? We don't have either of these special case issues. We're just going to look for top and bottom of bumps. That's where my derivative is 0. So right here, my derivative should be 0. And then what looks like right around x equals 0, I again have a derivative of 0. So these are the only 2 points in the graph of the derivative that I can plot exactly. So at x equals -2, the derivative is 0, meaning like its y value is 0. So I have essentially an x-intercept. And then again at x equals 0, I should have a y value of 0 right here. Okay, so now I'm going to take the 3 chunks of graph that these points have divided f into and make individual decisions about what the derivative is doing over those intervals. So we're always going from left to right. So we'll start at the leftmost point here. This is a decreasing function, right? We're decreasing left to right until we hit this low point at -2. So for that chunk of graph, f is decreasing, which we know means that its derivative is negative. So over here in the graph of its derivative, that means for x values less than -2, so over here on the far left side, I'm going to have negative outputs, so like negative y values. So I'm going to plot something down here. I don't quite know the shape yet, but I know the graph should be down here and not up here. Okay. And then for the piece between x equals -2 and 0, we are increasing left to right. So I have the opposite, right? Because f is increasing here, its derivative is positive, which means between x equals 0 and -2, the outputs of the derivative function are positive numbers. So we're somewhere up there and not below the x-axis. And then for this last piece, left to right, we are decreasing, which means its derivative should be negative. So to the right of 0, our graph of the derivative needs to be below the x-axis. All right, so now I need to kind of bravely sketch some sort of smooth graph that goes through these 2 points I've plotted and is down here, then up here, then down here. Roughly something like that will do. And again, it's a sketch. We don't know exactly how high this lump should go or how steep the rest of the shape should be. But as long as we're below, above, below, and we have these two x-intercepts shown, it's a perfectly good final answer. Let's try another one with that same way of thinking. So here we're asked to take the graph of f, sketch its derivative, and then also sketch the second derivative, which essentially will just be doing the exact same process again. So I'll start this one the same way as before, look for where the derivative is 0. That's going to be the bottom of a bump, which looks like roughly x equals 0 here. And then the top of a bump right here at x equals 2. So in the graph of the derivative, I can plot the x-intercepts at 0 and 2. And now I'll kind of take the 3 chunks of graph from left to right. So we have decreasing here, which means its derivative will be negative. So I'm going to be below the x-axis over here. Between 0 and 2, my graph is increasing, so its derivative will be positive, so we'll be above the x-axis. And then finally, we're decreasing here, so its derivative will be negative. And I end up with a fairly similar shape as the last example. Just something smooth that's below, above, below. And now to sketch the graph of the second derivative, I'm going to repeat the process using this as the original graph, right? Because this is just the derivative of this. So now I'll look at it with new eyes and say, okay, where is the derivative of this 0? That looks like it would be right here. Its derivative would be 0. So right at x equals 1, I'm going to plot an output of 0. Now we'll read the graph from left to right. We're increasing, increasing, increasing until 1. So its derivative will be positive. So that'll be kind of up above the x-axis here. And then after 1, it's decreasing. So its derivative should be negative. So we'll be below the axis down there. And we need just kind of the simplest, smoothest shape that's above, hits 0, and then goes below. Something like a straight line with a negative slope passing through that point would do. All right, let's do one more example in this video, which is kind of the weird example at the end here. So this graph, as advertised at the beginning, has some corners in it. And it's also composed of straight lines otherwise. So this ends up being a very bizarre derivative graph answer. Okay, so for this graph, there are no points where the derivative is exactly 0, right? There's no perfectly horizontal tangent line moments. But at this point right here, the derivative doesn't exist, and then same thing here. Essentially, if you did the limit definition of the derivative, you'd get a negative number from this side and a positive number from this side for their slopes. So because the two sides of the limit don't agree, it's a d-any. So that does give me some information about the image of the derivative, but it's not something that I can immediately graph. And if we look back kind of at this summary from the beginning, we said at a corner, it'll be a jump in the derivative graph, right? Where you have an abrupt change in slope. So that's what I'm going to anticipate. So at -2 and +1, an abrupt change in outputs for f prime. The other interesting thing here is we can be a little more specific about this graph sketch than we could for the other ones that we've done so far, because these are straight line segments in the graph. So the derivative of a straight line is the slope of that line. So when the graph is curvy, we're just kind of roughly eyeballing positive or negative slope. But when it's a perfectly straight line, we can compute exactly the slope as long as enough of the points are clearly marked, which they are here. All right, so let's first consider the leftmost part of this graph, right? So we're decreasing from left to right. So I know the derivative will be a negative number. But in fact, I can compute the exact slope of this line segment. I can see it goes through the point -2, 0. That's right here. And then another point looks like -3, +2. That's this point right here. And I can compute the slope between them, or you can eyeball it using the graph. Y value minus Y value over X value minus X value. I get -2. All right, so my derivative is going to be -2 all the way up until X equals -2. So I'm going to draw a perfectly straight line at height -2. And then at the corner, I'm anticipating a jump in the graph, right? So I shouldn't have any f prime graph at -2 because it doesn't exist. So I'm going to do an open circle and prepare for a jump. And then I'm going to repeat the process for this line segment. I say, all right, it's increasing left to right. So I assume it's going to be a positive slope, like we're going to be somewhere up here until 1. But I can compute exactly this derivative because it's the slope of this line. So for this one, I again have the point -2, 0. And then some other point on this line segment, 1, 2 looks pretty clear. The slope between those two is 2 over 3. So I'm going to come up here and say, all right, 2/3 is right about here. And I'm going to go from -2 to 1 with open dots at those jump points because the derivative graph just straight up does not exist there. And I'll repeat the process one more time. So for this line segment over here, again, it's decreasing. So we expect that we're going to jump down here somewhere, but we can get the exact Y value. So for this line segment, 1 point on it is 1, 2. Another clear point on it looks like 3, 0. I'll compute the slope. We get -1. So I'm going to go to a Y value of -1 for the derivative and abruptly jump to it at that point. And this is actually my completed derivative graph here. And again, you can see these corner points. We said the derivative won't exist. And as long as all of these guys are open circles, we've achieved that in the image.